Welcome back to the SETI Patent Podcast. I'm your host, SETI. In our last episode, we dove into the surprising performance of Tesla's FSD in China and what it might signal about their global strategy. Today, we're shifting focus to another fascinating Tesla endeavor, the Optimus humanoid robot. We've all seen the recent videos, Optimus showing off more refined hand movements, handling objects like eggs, even doing yoga poses. The visual progress is undeniable. But as a patent attorney focused on the underlying tech, my attention is drawn to something less visible, yet potentially far more crucial for Optimus's future: how it controls those movements so smoothly, especially considering the inherent delays in any complex system. What's the hidden technological leap enabling this agility? Could it be related to how Optimus perceives and interacts with time itself within its own system? Robots, like humans, don't act instantaneously. There's a delay, latency, between sensing the world, processing information, and executing a physical action. This latency exists in sensors, internal communication networks, like nerves, the AI brain doing the calculations, and the actuators, the muscles. Simply making parts faster isn't the whole story. My hypothesis, building on hints from Tesla's broader AI work, is that they're developing something I call Latency-Aware Behavior Modeling, or ELAB. The core idea is that Optimus isn't just trying to react quickly, it's actively measuring, predicting, and integrating these internal time delays into its very motion planning. It knows how long things take within its own body and plans accordingly. Why is this labby approach so critical? Think about human movement. Our brain constantly compensates for the time it takes nerve signals to travel and muscles to respond. It's why we can catch a ball smoothly. Now, imagine a pro baseball player whose predictive skills remain sharp, but whose reaction time slows even slightly. They start missing the ball. Prediction is useless without precisely timed execution, accounting for system delays. It's the same for robots. Without accounting for latency, movements become jerky, inaccurate, or unstable. A robot trying to quickly grasp an object might overshoot or fumble if its control system doesn't perfectly factor in the delay between seeing the object's position and its hand actually reaching it. Achieving fluid, human-like motion requires mastering these internal timings. Lab is the potential solution. So, how might Tesla be achieving this? This is where their deep experience with FSD becomes highly relevant. We discussed latency in FSD previously, but it's worth revisiting a specific patent, WO224039866A1. While focused on driving, it details sophisticated methods for dynamically modeling and compensating for latencies across the entire sensor-to-actuator pipeline in their vehicles. They even handle different latencies for steering versus acceleration. It's highly plausible Tesla is adapting these proven principles from the complex 2D world of driving to the even more challenging 3D world of humanoid robotics. They have the foundational expertise in precisely predicting and managing system delays in real-time, safety-critical applications. What about those teleoperation demos, where a human seems to be controlling Optimus remotely? Some might dismiss this, but technically, it's incredibly challenging. You have communication latency plus the robot's internal latency. Successful execution of tasks like picking up objects under these conditions strongly suggests it's not simple mirroring. I suspect the system is interpreting the operator's intentions, calculating the total combined latency, and then using its internal LAB model to generate an optimized, physically achievable movement for Optimus. The teleoperation might actually be a clever way to both demonstrate and further train these underlying latency-aware capabilities. If Tesla is truly mastering LAB for Optimus, the payoff is huge. Firstly, it unlocks far more natural, agile, and stable movement, crucial for robots operating in our world. Secondly, and perhaps more significantly for development speed, It means Tesla likely won't need entirely new control models every time they upgrade Optimus's hardware. They could potentially just update the latency characteristics of the new components and retrain the existing LAB model. This adaptability could drastically accelerate progress compared to traditional robotics development cycles. So, while the demos impress, I believe the real magic might be happening under the hood with latency-aware behavior modeling. It's this focus on intelligently managing physical constraints, leveraging their FSD experience, that could give Tesla a significant edge in the race to build capable humanoid robots and lead in the broader field of physical AI. It's definitely a space I'll be watching closely. That's my analysis for today. Thanks for joining me on the SETI Patent Podcast, and I'll catch you on the next one.